everyone, and I'm pleased to announce Professor Amit Kumar Mishra and his talk about calibration in an eye.
Hi, everyone. Let's start with what is calibration and why we require that. Some of the conventional approaches, because calibration is as old as electronics itself, and why AI makes sense to be used in calibration of sensors, limitations of AI for calibration, and then something called blind calibration. We start with that and then check how it works, and we'll end with a few different ways of doing blind calibration. That is one of my passions this last few years. We have been doing a lot of work in blind calibration in the last 3 to 4 years. We have put one patent and a couple of journal papers in that. Okay, so what and why? Why do we need calibrations? People tell that, okay, data is the new oil and data is the new Autobahn of the industry 4.0 and things like that. Where do we get data from? What exactly are data? Data represent some physical reality, right? Data are just numbers, but numbers as such have no meaning. Numbers have to represent something. So numbers represent some physical reality. How do we link physics and numbers? That is through an entity called sensors. So sensors transfer a physical quantity to electrical quantity. The umbrella term is transducers. We'll not go into that, but sensors is good enough. I had a nice cartoon. I hope it is there. Yes. I do not know if you have read this poem. It's also there in Ice Age 1, or Ice Age 2. I watch a lot of movies. So it's like water, water everywhere, not a drop to drink. So when you're stuck in sea, you have a lot of water, but it's useless, which is salt water. Similarly, what is happening of late is that the cost of sensors has been going down. So it's cheaper to buy sensors. The skills required to install a sensor is going down. So every Tom, Dick, and Harry can buy sensors and put in the so-called IoT, which itself is a disgrace in terms of terminologies. And they collect data, and the data is everywhere. But is the data reliable? The data is not doing its job, which was to represent some physical reality. Then it's useless data. So that is a question that many people kind of tend to forget. So data is everywhere, but the bytes are not trustworthy. And I should put in context, because you guys are interested in space. So for a space payload, for example, if I'm designing a radar or an electro-optical system or a hyperspectral camera for satellites, almost 10 to 20% of the budget of that sensor design goes into what is called calibration validation. I'll give some examples. Again, I'll divert given that it's a space community. So my first job after PhD was in India, and one of the Indian Institute of Technologies. And that was 2006 to 2011. 2006 to 2008 was when Indian Space Research was designing its first radar satellite. So my own area of expertise is in radar. So I was working on some projects in that bigger project where they were designing radars for space. And they did a very good job, but the problem was that it was kind of a bit in a hurry. So they didn't put enough effort in terms of calibration validation. So when the satellite was sent, it was sending pictures. Pictures look nice. Pictures are comparable to what you'll see in optical pictures, but they were not carrying the information that we wanted them to carry, because the calibration phase has been kind of, I won't say it was bad, but there were issues in that. So instead of putting 20% of the budget into calibration, they thought that they could get away with lower than that. So my point is that any sensor out there, it has to be calibrated, especially space sensors. They have to be calibrated and validated really well. And another example. So because I worked for as a consultant for in space research for some time, and my area is radar. One of the success of Indian space was sending that vehicle to moon. And one of the things that that satellite did in moon is collect radar data of the lunar craters. And the craters are dark because lack of sunlight, can't see into the crater, but you can collect radar data. And the radar signature of whatever inside matched with water or ice. So that was one of the first confirmatory proof that there is ice inside lunar craters, most probably. But again, those sensors were not really calibrated and validated so well, and that is why there is some doubt. And that is why the radars were again sent in the second mission, what they were Chandrayaan-2. And yeah. What is calibration? Calibration is to make sure that the data is phenomenologically correct as much as possible. Have you heard of this word, phenomenology? So anyone interested in old Greek philosophy, like that of Plato and things like that? So Plato has this story. Plato says that the situation of human beings is like somebody trapped in a cave. So imagine that you're trapped in a cave. You cannot see what is going on outside, but there is a small hole in the cave through which sunlight comes and creates shadows on the cave wall. So from that those shadows, you can see things, and from that, you want to understand what is going on outside. So that is famous Plato's allegory. So showing that is how human beings, we try to make sense of things. So phenomenology basically means modeling the phenomena or the linking to phenomena. So for example, when you do some sensing, there are again numbers. From those numbers, how do you understand the phenomena? So to build that information is calibration. Okay, why it is required, why it is important. If your data is not reliable, then data is sometimes used to in the control algorithm to control things. For example, your spacecraft is going and it has got some sensors, some gyrometers through which it can measure if it is on the trajectory or not. And based on that, it can actuate some propulsions so that it is back into the right trajectory, right? So sensors creates data. Data goes to a control algorithm, and that creates actuation. If your sensors are not giving the right examples, right data, that can create big problems. So as an example, this is a famous example of lack of calibration. 2018 and 19, two Boeing MAX 8 aircraft crashed, resulting in total of 346 fatalities. Investigations revealed that both planes fell to the ground under similar circumstances, and an incorrect sensor reading erroneously activated the aircraft's new flight control system. So the point is that if sensors are not properly calibrated, in the most benign case, let's say your CO2 sensor is not giving right reading, you hardly see CO2 values in a city. But in drastic cases, this kind of things can actually happen as well. Another case, so there are two labs from the States. They wanted to build air quality monitoring systems in Malawi. So they got, and mostly air quality has got two major parameters, carbon dioxide and PM, particulate material. So they built the sensors in their lab, calibrated them back in the States and brought them to Malawi. Now, when they brought them to Malawi, the sensors were not working properly at all. That had mainly two reasons. Number one, they kind of missed that Malawi is a tropical country. So it has got lots of humidity. Humidity drastically interferes the reading coming from carbon dioxide monitors, sensors. Secondly, most Malawian villages, they rely on burning wood to cook. So that creates a lot of fume. That also affects the reliability of CO2 and PM 2.5 sensors. So again, that's also one of the very few papers who actually accept that the lack of calibration resulted in quite drastic implications. Some basic maths. Many times speakers in conferences say that this is the maths you will see, but you will see more maths later. again, there are some kind of definitions. So measure the true value of interest, let's call it X. Output from the sensor is Y. And observation process is F. So F is the physics of the sensor. So you want to measure X, let us say the concentration of carbon dioxide. That's the physical real quantity. How do you measure that? So you can have different physics, like most of the CO2 sensors you can buy of the self. They use infrared based, I forgot the exact word. So they send these infrared rays and they see what the dispersion is happening. From that, they try to estimate the concentration of CO2. So that is the physics observation process. CO2 is what you want to measure. That's the physics process. Let us call it F. And then you get the reading Y. Now you want that Y should be equal to X. But this is the process that is involved here. Now, unless you understand F, again, this is a noise part, and the noise part is everywhere. We will not go into this part. I have this standing joke when I teach about noise analysis. Like, I do not know if God is everywhere, but noise is everywhere. So you can't avoid that. So the opposite of that is called restitution process or calibration process, i.e., you have the reading, whatever the meters shows. From that, you want to find out what is the exact X. Right? So X is what you want to measure. It goes through a process and you read, okay, 220 ppm. But maybe that is not correct. So from that 220 ppm that you read, what is the actual X? So that is the calibration process. The calibration process inherently assumes that your sensor is not working properly, which means that when you got a fresh sensor made in lab, that should be calibrated. It should be reliable. So far, okay? You're the same page? Good. If you think we want to find out F inverse. So F is the observation process. We want to find F inverse. Now, have you been exposed to things like Laplace transform or jet transform a little bit? What is the inherent issue in this thing, estimate F inverse? Because F can be something very simple. Let us say F is equal to mx plus c, straight line. F inverse 1 by mx plus c. Then what will happen is that to expand that in Taylor series, that will involve all the powers of x. So estimating an inverse function is always an impossible task. You can only estimate that to a certain degree of accuracy, not beyond that. Because when you say 1 by some function, you can immediately expand that in Taylor series, you'll get infinite powers. So first thing is that calibration is an inherently impossible task. But then everything in engineering is. Like, engineering is all about taking the right assumptions that will make things work. Sometimes students ask, what is different between science and engineering? Science is all about knowing the truth. We don't have the truth. As long as your thing works, nobody's going to ask, is it following some true principle or not? Make your things work. That's all we care about. So as long as my sensor is giving me good enough data so that my plane doesn't crash, I'm happy. So this is one problem, but not really a big problem for us. Some definition from the standards. I will not read through them. I just put it there for like a minute or so. You can have a look at that. Calibration is a well standardized process. So every sensor in every domain, they have to be calibrated. They follow certain process. They follow some standards. And the issue is that most sensors, once you have calibrated in the lab, bring to the field, start operating, they have something called drift. So the reliability starts changing slowly. Hence, most industrial sensors have to be calibrated once certain number of months. So that is always a nuisance. Similarly, for any kind of airborne or spaceborne sensors, they also have to be calibrated. Now, I will give an example of a radar because that's what I know. Let us say you have put a radar and a satellite, spaceborne radar. You want to calibrate that. You want to make sure that whatever reading you are getting sent to you through telemetry is actually the correct reading. How can you calibrate a radar in the space? No answer is wrong answer. The calibration means you should have something that you already know what is the right value. Okay, forget radar. Let us say you have a temperature sensor. You want to calibrate that. How can you calibrate that? Is there any temperature that you are assured of that, yes, this is 40 degrees always? Is there a phenomenon like that you are assured that, yes, this is that temperature? Boiling temperature of water. So water at sea level will always boil at 100 degrees, right? So if you have got your new temperature sensor, bring that deep into boiling water and see if it is reading 100 degrees. If it is not, then number one conclusion, it is not correct. Then the question comes, okay, if it is not correct, how do we fix it? But again, the first step is knowing that it is not correct. So what we just did there, so we found a temperature or a process whose temperature we already know. And then we compared that with the reading of the sensor. So that is called one-point calibration. Similarly, gravity is 1g at surface of Earth. That everybody knows. So let us say you have a pendulum, you swing it. If you know the length exactly, you can predict the period exactly, assuming that you know g, right? So this is another thing we do. Many people nowadays use these inexpensive vehicular radars because they're so cheap and do many kind of things. How do you make sure that the data it is giving you is correct? Because the radar doesn't give you optical data. If it is optical data, you can see, yes, there is a crow there, or there is a ball there. But if it is not optical data, we cannot directly see. So one of the easy ways to calibrate or to see that your radar data is correct is to make a simple pendulum with a metallic sphere and swing it. If you know the length, then you exactly know its speed. And you can match it with what is the speed that your radar is saying. And then you can do that. If your functions, you remember those functions linking x with y? If the functions are linear like this, then any, so linear functions are the best. But as it gets more and more nonlinear, things get complicated. So if you want to estimate a straight line, how many readings do we need? A straight line mx plus c, two variables. We just need two reference points. But as and when the line starts getting more complicated, you need more number of readings. So the most basic part, if y equal to just mx, so it's a straight line only. Then if there is any problem with that, we can check with a single point which you are assured of, and then fix that. That's called a bias error. And that is called one-point calibration. If it is more complicated, you can have two-point calibration if it is mx plus c. And similarly, you can be 3-point, 4-point calibration. The catch here is that for this kind of calibration, you need to know certain phenomena which readings, observations, you know exactly. If you do not know that, then it's tricky. Now, so we have seen a little bit of what is calibration, some very basics. Again, there are like full courses on calibration. I'm not even assume that I can provide all the information. If you look for look in Google Scholar for AI for calibration, there are like loads of papers. Now, why is like that? Because we have seen that calibration is basically estimating the restitution process. So calibration is basically trying to find out F inverse. So it is estimating a function. There is a nice theorem in neural networks called universal approximation theorem. What it says is that a single hidden layer neural network is good enough to model any kind of function in the world. Your function can be any complicated, doesn't matter. A single hidden layer neural network can model that. This is the law from ANN. Now, what is calibration? Is estimating function. So the match is quite clear, right? Your law in ANN says that ANN can model any function. Calibration is basically modeling a function. Put 1 plus 1 equal to 2. So that is why you find lots and lots and lots and lots and lots of paper on using AI for calibration. Okay. So that's the more mathematical wording of that theorem I just mentioned. A single hidden layer based feed-forward architecture is capable of approximating any continuous function within any two Euclidean space. This people often don't mention, but trust me, this is very important. You have to make sure that your space is Euclidean. I'll give an example. So I'm assuming that all of you know a bit of statistics. Okay? In statistics, let us say your data is multidimensional and the data is Gaussian. So if it is single dimensional, it has got two parameters, mean and variance. If it is multidimensional, what are the equivalent of mean and variance? If it is multiple dimension, so every data point is a vector. So the mean will be a vector again. And variance becomes a covariance matrix. So all of you have heard of covariance matrix? Covariance matrix. It's a statistically very significant thing. Now, covariance matrix as an entity does not lie on the Euclidean space. Covariance matrices lie on a conical space. I just want to mention that if people often miss or forget to mention this thing, but then non-Euclidean spaces are actually more common than what we think. Anyway, okay. I'll just give some examples. Let us say this is a complicated function. You want to model that using ANN. If you have one such network, it is represented. It models this function, this one, this function. You can keep adding more and more neurons, and you can start getting interesting functions. Basically, the thumb rule is that the number of nodes in the hidden layer is equal to the number of steps. So 4 nodes, 4 steps. Again, put more number of nodes, you can start approximating, because this basically says that you can have some linear approximation of any function. So you increase the number of nodes, you can approximate any complicated function. So hence, the point is that you can use ANN to model any kind of function, and calibration at its core is a function estimation task. Hence, you can use ANN to do calibration. It's just a screenshot of lots and lots and lots of papers on using AI for calibration. Now, when you see too many papers on one topic, you can safely conclude that most of these papers are useless. Because it's so easy to publish, they just take some data and publish something. So when you see so many papers, one thing is that, I've told that a sensor you take and start using, with time it drifts. So its characteristics drift, and hence it starts giving you wrong data. And let us say you have designed a machine learning algorithm which can fix it. So you have designed an algorithm, and it can fix or can calibrate the data from the sensor. Now, what is the guarantee that that algorithm will keep working nicely for months together? None of these papers look at that. In fact, and it's an obvious question. If you think scientifically, for example, if you want to use that algorithm in your factory, you will want to be assured that you don't have to go and again fix it. So pragmatically speaking, that's the correct question. But none of these things answered that thing. And plus, interesting that This is the paper we published on calibration. Not a great work. The only thing that is new in here is that we showed how do the efficiency of AI calibration algorithms deteriorate with time, which was not at all touched before. Anyway, okay, how do we calibrate? So you need to have a reference point, price for you as well later, to get it working. What if we do not have the reference labels? So that non-thing is called reference. So if there is a reference, that's fine. And how do you get the reference done? So 2 ways. As they say, take the mountain to mammoth or take mammoth to mountain. So either you take your sensor to lab and calibrate, or you take a fully calibrated sensor and take it to your factory where things are running. There is no other way. Now, the question is a reference absolutely necessary? A reference gives some kind of invariability. So that thing that's true value. So that started this new way of research called blind calibration. So in blind calibration, you don't have to get a reference sensor. So you should be able to calibrate the sensor without taking it to the lab or getting something to the factory. Sounds exciting, but there is no free lunch in life, right? There's always a catch. We'll come to the catch later. How do you do that? Now, if you cannot take the sensor out, if you cannot take anything to the factory, you can then think, okay, given this sensing thing, what is invariable? What is not going to change? I know that my sensor is going to drift. It is going to give me bad data. Is there anything else that I can rely on that is going to make me confident? Okay, even if the sensor is drifting, I'll check, okay, how far this has changed. If this thing that should not change has changed, I make sure that this is back to unchanged thing and thereby fixing the sensor. So this is where I've got pictures, but it's better to tell before that. I could have drawn something. So let us say you have got data whose dimension is 3, XYZ. Okay. So you have got a lot of data like that. And all the data, because it's 3 dimension, they lie in the 3-dimensional space. Now, let us assume that out of the 3 dimensions, 1 is redundant. So x, y, g, right? But z equal to x plus 2, 1. So it actually depends on x and y only. That's another dimension, but it is not independent. How would that data look like in 3 dimensions? So in a way, if you think just intuitively, you don't have to be an expert of geometry to understand that. There are 3 dimensions, x, y, z, but g is equal to x plus 2, 1. So g is useless. So the data actually have only 2 variables. If there are 2 variables, the data will be lying in a space or in a plane. In a plane. Right. So even though there are x, y, g, the actual data recorded, they all lie on a plane. Right? So that was the first paper on blind calibration. They assumed that, okay, let us do one thing. Let us put too many sensors. So let us say there is something that you want to sense, and that has got 5 dimensions, but we will put 10 sensors. So 5 actual dimensions, you have got 10 sensors. So every time those 10 sensors are recorded in a vector of dimension 10, but the 10 dimensions are not useful. The only 5 is useful. So in a way, let's go back to our 2 or 3 dimensions. It's easy to visualize. So you have 3 sensors, only 2 dimensions for the actual data. So all the data you record by the 3 sensors, they will lie in a plane, right? So you start your recording process, your sensors are all fresh. So they start giving some data, and all the data lie on this plane. Now the sensors can start drifting, but the fact that they should be on one plane will be remaining true, right? So what you can do is that this plane is your invariable truth. When individual sensors start drifting, they will start, it's like jumping from that plane. So when you see, okay, let's say 20 sensors, they're all lying on this plane to start with. with time, we find that, okay, sensor number 5 is not on the plane anymore. Why is that? It's not that the plane is correct. So the sensor number 5 should be incorrect. So you try to fix sensor number 5 so that it is back on the plane. So that becomes the calibration process. The individual sensor starts jumping out, you bring them back together. Nothing works forever, of course. You work for some time, but at least some time is good. So yeah, that was the first paper. The inventor was Balzano. And after that, his paper and similar kind of idea, once you introduce a new idea that, okay, look for some invariable thing and make sure that that invariability is retained. And then you fix your individual sensors to make sure that the invariable thing that does not change. And then there are lots of papers on this idea. Yes.
These are there number of same type of sensor?
Yes, same.
Yes. Okay. They're not different types of sensors.
Same sensors. The only thing is that there are too many sensors. So there is oversampling of data. And hence, with oversampling, you are assured that your actual data lies in a subspace and the actual full space.
But they're all
same.
Looking at the same thing.
Yes. Same. Yes. Let's say temperature sensor. So again, these are easy to implement in certain applications, not all the applications. For example, if you are sending a radar to space, you can't have 10 radars. It will mean 10 times the cost. But if you have like implementing temperature sensor, for example, so I work with an aluminum manufacturing company in Sweden called APT. One of their pain point is their pyrometer. The pyrometer is an IR image-based temperature sensor that they use that to measure the temperature of molten aluminum so that they can predict the quality of aluminum. The problem is that pyrometer as a sensor is quite unreliable. Its reading can change with everything. Its reading can change with the surface temperature, with the surface color, with the surface texture. So they want us to work on some algorithm to make sure that the pyrometer reading is more reliable. So, but again, pyrometers are not that costly. They're not radar costly. So we can actually, that's what we are trying to do. We are trying to have multiple pyrometers looking at the same region of interest and trying to see if we can implement things like this. Another interesting idea, it came from a Chinese group. So what they say is that, okay, let us start with, again, more than one sensor. Let us say 5 sensors. We know that they all will start drifting, but they will not all start drifting at the same time. So if we start 5 sensors reading the same thing, we start tracking them. And whenever one of them starts moving away, you make sure that it is brought back to where it should be with its friends. Very simple. And again, how you do that, how do the tracking, those things require interesting algorithms. But as a core principle, it's very easy. I was surprised that a company in the States, so I met these guys in a conference. So these guys make a sensing solution for the Atomic Energy Agency in the USA. And they have been trying this algorithm. Of course, the exact algorithm they will not tell me, but in principle, this one. And they have been trying to fix some sensors in atomic reactors for last 18 months. And they have not been needed to calibrate them for 18 months. And that's a very substantial validation that yes, this kind of things can work. Let me see the time. I can tell a joke if you want. Knock, knock. Doctor. Doctor. Okay. So then based on that, I developed some algorithms. I will not go through them. But that is where they start getting more mathy, and I don't want you to get get brain dead at the end of the day. But let's go to an interesting thing again. Yeah. Have you all been exposed to things like eigenvectors and eigenvalues? I'll make sure that you get. Okay, let's come to the more easy to understand things. Nowadays, anything to do with AI is actually easier to understand because you don't have to understand the math behind the AI. So let me directly go to the AI part. So this is a patent that we filed. I filed 2 years back. We have been since experimenting on this idea. So again, the idea is that you try to find out something that does not change, or at least does not change as much as the sensing physics itself. So what I do here is that this whole sensing process I break into 2 stages. The first stage is, so this is the perturbation, the starting point of the disturbance. It comes through the environment to the interface between your sensor and your devices. And this is what exactly you want to read. And your observation process, and you read this. So calibration is estimating this from this. Now the point is that with time, this thing starts drifting. But are there cases in which this thing does not change? So for example, the main idea I had was for measuring air quality. So if I'm measuring air quality for a given season, if there are no major changes in the surface, like no new buildings or no trees have been cut, then this environment remains more or less the same. I can assume that the environment is same or similar. And it is more valid in cases like in industries. In industries, they try to maintain the environment. So this environment can be assumed to be consistent. So the way we start is that how much you guys know about machine learning? Has there been any course on machine learning? Yeah, oh, good. So you know about autoencoders or encoder decoders. That's fine. That's enough. So in encoder decoder, the good thing is that you don't need a ground truth. In encoder decoder, you give an input and you are recreating the same input, right? This is what it does. So basically, I'm using an encoder decoder network, but it has got an intermediate stage. It has got one stage representing the calibration and one block representing the environment. To start with, I have got calibrated sensors. So I know what the sensor is reading, and what the actual value is. So in the initial stage, I collect a lot of data. I put into encoder decoder. But in the encoder decoder part, I have got this input I want to recreate here, but I also know this one because this one is calibrated. So I have got another thing that I have to find. So if you remember, in encoder decoder, you have got one error function. So your input versus what you are creating. In this case, I have got two error functions. One is the outer error and another is the inner error. So once it has been trained and errors are minimized, that's fine, it's been trained. Then starts the calibration stage when I'm assuming that these things start to drift. So what I do is that after they have drifted, I've got new set of data. I again put them through encoder decoder, but in this time, I freeze this part because I'm assuming that the environment does not change. So only this part can be changed. So when you have trained the encoder decoder with new data from the drifted sensor, you start fixing this part. And once it has been trained, you take only this block. This block is basically a bunch of A and N inside. So you put some input, you get some output. This actually works as the calibrator. So quite easy to understand, very easy to implement. It's like 5-6 lines of code if you are starting to use Keras. It actually has shown some good results, both in simulation and when you started testing it with real data. Our source of real data is our sensors in Cape Point. So we designed some hardware sensors on our own, CO2 and PM. And in Cape Town, in the Cape Point, the Met Office maintains its own sensors, and they follow all the international standards, very highly calibrated, very costly, and all those things. So we use those as our ground truth. So we get very good data set to keep trying different algorithms and see how they behave. And yeah, so they have shown some good results so far. Next, I'm trying to see if I can use the same thing for the aluminum company in Sweden. I'm a bit nervous about it, but we'll see how it goes. Okay. Again, simulation results, I will not bore with those things. Another thing. So again, taking from the encoder decoder part, this was a simpler encoder decoder. If you start thinking of VA, then you also need to make sure that your sparse space is following Gaussian distribution. So you have to find the KL divergence there, so you get another error function there. Now, the sparse space is an interesting thing because sparse space in encoder decoder, they represent the gist of the data. So what we have seen is that if you start looking at the distribution function of the sparse space, they can give you indications when sensors start drifting. So again, this is very new work. I haven't done much work, so I'll not present much. But this is the idea that if you look at the distribution of data in the sparse space, you can find interesting deviations from the normal distribution when the sensors start drifting. We'll see how it goes. Okay. This is another thing I wanted to think. Okay, again, we can discuss about information a little bit later. So I'm assuming that most of you are in the downlink side of space technology. So in downlink side, data is an important thing. So one important figure of merit is called signal to noise ratio. So how much signal is there, how much noise is there. But to be very fair, signal as it is not of much interest. Unless your signal can be used to do something interesting, it's not going to be very interesting, right? So that is why signal per se is not really what we need. We need information. So I'm working on a new framework that I'm calling information to noise ratio instead of just signal to noise ratio. And information, interestingly, depends on your application, right? So given a different application, something can be information for you. So for example, let us say, what will be a good example? Let's say you are going to clean the grasses. Then your tree, if you take a picture, the tree is like noise for you, but the grass is actually information for you. But the other time, let's say you are designing some pruning algorithm for the trees, and the grass is noise, and the tree actually is of information. So depending on application, your information's definition changes. But thankfully, we have got some very good definitions. We can say mathematical framework that we can use, and I have been exploring two ways. One is Fisher information that depends on estimation theory. And another one is minimum description length, which is based on information as defined by Kolmogorov complexity. We'll not go into that. Don't get scared. Okay. Skip this one. So let's think to the end of the talk. Let's take some questions. I hope there are questions.
Okay. Have you any questions? I have questions. The first question is, we calibrate sensor or we calibrate data?
Sensors,
Not data?
not data. Usually not data, but
But you manipulate with data,
yeah,
not a sensor.
no. So
That is, in my opinion, what you are doing, you are calibrating the data. Because you have no possibility to calibrate sensors, because a calibrate sensor means that your sensor operate in the determined environment.
Yes.
But you have the data, which is a real data, and you have the reference data to calibrate the data that you calibrate data.
Yes, for that.
This is a big difference about that. Yeah, that if you use algebra or artificial intelligence doesn't matter, but you calibrate the data because you deal with the data. This. But also for us, this is not important. The data. Important is the knowledge which we can extract from data. What is data? Nothing, yeah? Not value of data.
Just numbers.
The knowledge, how to extract the knowledge from the data. This is a question. Do you deal with such a problem?
So this follows the classical understanding of human understanding, where they put data, information, DIKW, knowledge and wisdom. So data to information is, I will not say easy, but relatively easy. Then information to knowledge, that extraction is an interesting thing. And computer
This is
science,
a crucial point
Yes.
of the analysis of the spelling data. This is how to transform this information
Data to
to the knowledge.
Yes.
Yeah? Because the students are reading a lot of text, a lot of papers. You said don't read the papers, that you understand. But they have a lot of information. But what is information? They need to have the knowledge. Yes. This is, in my opinion, a crucial problem for space data.
I think that's a very good
But
point.
I think Michał has completely different view on that. But yeah, Michał, you have the same?
I do not want to interrupt that philosophical discussion. I have another question, but
Please.
the last.
Sure.
Yeah, so referring to very good presentation, I would say. What was because you started that and suddenly you didn't mention, but how you achieved the calibration of radar sensors?
Okay.
Yes. This is something that I would like to know. Like, what was the reference data for that?
Yes. So in radar sensors, radar measures what is called radar cross section, RCS. And the RCS is representative of the dielectric constant. So if the RCS is correct, the dielectric constant measurement is correct. So the way to do it is you design a non-reflector of a non-dielectric constant and you put on the ground. And when the radar goes over, it measures that. And then you compare the phase, what it measures and what it should be. You know, and again, people mostly, not people, like I know some people tend to forget that lot of telecommunication and remote sensing leverages on Maxwell's equations. But Maxwell's equations are heuristic. They are not really driven on derivations. So they are based on observation and heuristics. Hence, if you look at the RCS of most objects, they are numerical. The only object which RCS is non-mathematically is a sphere. Even a simple plate, RCS is not non-exactly mathematically. So, but again, in terms of canonical reflectors, or like reflectors which RCS we more or less know, things like corner reflectors are very common. So you put like a big aluminum sheet that like with a corner, and then when you get the satellite reading or the radar reading, you know exactly what it should. When it is not matching what it should, you know how to fix it.
Like a kind of like a scatterer?
Yeah, a non-scatterer. Yes. And again, depending on the frequency, it can be big. We are consulting a company in Netherlands which was building a radar again for airborne radar, not space radar. A very high, very low frequency. When it's a low frequency, the lambda is long. When the lambda is long, the corner reflector size is big. It has to be at least 7 to 10 lambda. So that becomes a very difficult task. So the innovation that our PhD student did was to make something called graded corner reflector. It's not new per se, But making graded corner reflector for calibration was an interesting thing. But yeah.
Okay, thank you.
Okay.
Professor, this approach, will it work for the first time measurement also? What I understand is it can be done somewhere else and can be applied to a real system. Yes. So what if my environment itself I'm measuring for the first time?
You have no reference. Then you have to make sure that, as Professor told, the hardware has to be perfect. If the hardware is not reliable, then we have nothing to go by.
There I cannot use the data.
No. But then if I have full faith on my hardware, like when they sent Chandrayaan and they had faith in that, and when they got the RCS, oh, the RCS looks like ice. It has to be ice. Yeah.
One question. I have one. Information measure. The B. Fisher measure. Before the calibration and after calibration, what is the difference?
There is no work on that, but that's a good point, because then we can use that, because
For instance, we use a singular value decomposition.
yeah.
We choose one singular value for analysis. That means that we reduce the information.
depends how we define and fish information.
Yeah, that if you are doing, for instance, PCA, that we choose only the part of data. That it's a information measure is going down.
Yeah, but then information defined by what? So if information is captured by the fourth and fifth principal component, then other things are not information. Like they did this experiment in facial recognition. Usually they go by the highest eigenvalue principal components. But they found that for face recognition, the first and second PC, they are showing just the shape of the face. That's round for all of us. So for recognizing people, that's not so useful. So they discounted
128 features to recognize
that's
the
right.
head. Very bad.
So again,
This is the number of information.
Yes. That's exactly where your simple signal to noise ratio will tell that just take the highest principal components. But as you told, information, if you look at that, then we find, okay, maybe we have to focus on some other component and not just the big is not always better, so to speak.
Because sometimes there is additional information you don't know about that. It's better to manipulate with raw data that's calibrated data. For qualitative analysis, sometimes the raw data is much more informative that's calibrated data.
Yes.
Okay. I am not a specialist in data analysis with calibration with sensor, but that is only remarks. We hope?
No, yet.
Okay, thank you, Professor.